In this video, we'll just briefly talk about how to apply the thin wall concept, and also to deal with something von Mises and something about the cracks, or the behaviors of a certain cracks. So let's just check it out. Right, we have a pipeline that has a diameter of 0.6 meter. Alright, and normally you need to know that whether is this a outer diameter or radius or a inner diameter. In this case, it's actually an outer one. Alright, we're actually not informed, but never mind. So 0.3 meter is our radius. Alright, is outer is equal to 0.3 meter. Alright, or you can also use the diameter itself equals to 0.6 meter. Alright, and we have a thickness of 1 cm. So 1 cm is 0.001, I think. Yeah, so your thickness is actually equals to 0.001. So 0.6, so this is in terms of meters now. So if we were to do that, what we have is, it should be 0.01. Alright, once 1 cm divided by 100 is actually 0.01. Okay, but anyway, this is the thickness. So 0.6 divided by 0.01, what you have is 60, which is actually larger or equals to 10. I mean larger than 10. Okay, so therefore we can use thin wall because it's larger than 10. Okay, so therefore let's do it. Alright, or you have to visualize your 0.6 meter. This is your very thin 0.01 meter thickness. Alright, this is why we talk about it is a thin vessels, that type of thing. Alright, at least you can visualize that I'm doing in terms of a thin vessel. Alright, and we have a pressure of 60 bar above atmospheric pressure, and is located outdoors with a paint coating to prevent corrosion. Okay, fine. So we have a gas that is within itself, so talking about the internal pressure. But in our case, we often assume that if there is a pressure interior, we assume that the pressure outside is equals to 0. Alright, so therefore we'll just talk about the pressure inside, and that's it. Alright, and therefore calculate the 3 principal stresses in the pressure vessel. And you may wonder why suddenly principal stress come in when we're talking about the vessel. Right, principal stress is because stresses over here are principal stress. Alright, and what we have been doing so far for what I've been doing is in terms of sigma, radial stress, the theta, and the longitudinal one, right? 0, 0, 0, 0, 0, 0. Alright, because in terms of pressure, in terms of vessel pressure and things like that, you're talking about containing a certain object, right, where you have a certain normal stresses acting on it throughout all this. And if you have to visualize this is actually your hydrostatic stress. Your hydrostatic stress is also in terms of this thing, right? Just all the normal stresses. Alright, because the hydrostatic stress will not actually cause your system to shear. Alright, that's all. Okay, let's continue first. Alright, so we know that we can assume that what we have been doing so far, all of them are in terms of hydrostatic stress type of stuff. And we know that in terms of a thin wall, the radial stress is actually equals to 0. Right? The radial stress is exactly the same as the outside pressure. But we assume that the outside pressure, which is PO, is equals to 0, and therefore there will be no reaction force to it also. Alright, now we have sigma theta and sigma zz. Alright, now how do we calculate it? We have our formula over here, sigma theta, and our sigma zz, and we know that radial stress is equals to 0 for thin wall, just to show you. So let's pay this formula, and we have pressure of what? 60 bar. We have a 60 bar pressure. 1 bar is 1 times 10 to the power of 5. So 60 bar is just 60 times 10 to the power of 5, or 6 times 10 to the power of 6, or is equals to 6 MPa. Okay? As for radius, alright, the radius over here, alright, I can actually use the outer radius. Alright, you can also use internal radius, but in our case, I'll just use the outer one. Alright, sigma theta is equals to my pressure 6 times 10, 6, multiplied by my radius, which is 0.6 divided by 2, because our outer diameter is given as 0.6 over here. Alright, your diameter, and then divided by your thickness. Your thickness is actually 0.01, which is calculated just now, right? 1 is 1 cm. Our thickness is 1 cm over here, as you can see. And then divided by 100, because change to meter is divided by 100. And what you have is 180 MPa. Okay, now as for sigma ZZ, the longitudinal stress, just now is a hoop stress. It's just hoop stress is PR over T. Our longitudinal is PR over 2T, so it's 2 times 0.01. The rest are the same over here. And what we have is a 90 MPa. Alright, it's 2 times. And therefore I can write my principal stress as 180 and 90 MPa, where this is 0, 0 because no shear stress. This is our theta theta, and this is my ZZ. Alright, so far so good. We just check it out. Okay, so this is it in terms of the MPa. I mean, maybe not. Alright, because 6 times 10 to the power 6 should be pre-A. Alright, should be PA. My fault actually. So yeah. Wait. Oh yeah, MPa. Sorry, MPa. Because yeah. Anyway, you can just sub it in, and then you'll know what I mean. Alright. Now, this is to get the principal stress, right? We have already shown you the principal stress that is over here. This is your principal stress, 180 and 90. Alright, where this is your sigma theta theta, this is your sigma ZZ, or your longitudinal stress. Alright, next, if the steel has a plane stress fracture toughness of 50 MPa square meter, then you find the critical length. Alright, how do we do this? If you remember back in way back on the videos, KIC, which is your fracture toughness, is equals to your sigma 1 times the pi a square root. Alright, where this is your A is your crack length. Alright, we know that our fracture toughness now in this case is 50 MPa. Alright, 50 MPa square meter. So since we know our stress over here, the largest stress is 180 because it's actually pulling as a tensile stress now. Alright, and therefore is equals to 180 square root pi a is equals to 50 times 10 to the power 6. Alright, and then I'll just rearrange. I'll have A is equals to 24.56 millimeter, and this is our crack length. Alright, and if you were to just zoom in a little, this is your A is equals to 24.56. Any crack larger than this, your stress, you're gonna rip this piece apart. Alright, you're gonna rip this piece apart. And just to visualize, because in fact we have been shown over here that this is also 24.56, and we don't know what the hell is going on, right? So therefore I'll just show you. No, not him. Yes, this one. So let me copy this picture, paste it here. Okay, so just now we have said that there will be a tensile stress. In our case is our hoop stress, right? Because it's the largest. Right, the hoop stress is 180 sigma theta theta. Alright, and therefore if I were to draw now, alright, this is actually in this particular plane. Alright, talking about just one slice of this. Alright, if I were to zoom out, alright, if I were to zoom out this thing, okay, hold on, and simply go into 3D. Alright, 3D is something like that. Okay, maybe not something like that, and then something like this. Then we have a certain path over here. Alright, so you can see that this is our crack over here. Alright, this crack is actually over here. I don't know whether you can see it. Somewhere over here is somewhat symmetry. Alright, maybe I draw it again. Yeah, something like that. Alright, so the crack itself is actually somewhat like this. Alright, it's axissymmetry, like axissymmetry. Alright, so if you were to look into this direction now, alright, what you'll be seeing is this one. Alright, this particular the point over here. So normally what we are counting is always this one, but in fact in actual fact, if you were to zoom it out, alright, it's in fact some form of a 3D type of a crack. Alright, this crack is coming out over here. Alright, that's to visualize. Alright, but however, we haven't solved for whether can our stress tahan. Alright, what I mean is that because we found our crack length already, find your critical crack length, but state whether you would be happy with this value. Alright, how can I be happy? How can I be very happy? Alright, I need to calculate something, right? So you need to apply the von Mises stress. Alright, we're gonna apply the von Mises stress. Because for a steel, its fracture point is talking about its yield strength. Alright, for steel, its fracture point is talking about yield strength. And in fact, yield stress is over here. Your yield strength is over here. Our fracture point must be here, right? Why do we take the yield strength? Why don't we take the fracture point or the fracture toughness of your material? Why do you take the yield strength of the material? I will leave you to think about it because I also don't know. Alright? To use von Mises stress, then you're gonna just use this apply this formula will do. Alright, where sigma 1, sigma 2, sigma. So this sigma 1, 2, 3 is just simply your radial stress, your theta, and your sigma zz. Alright, your stuff. And we know that this is 0, so we only have sigma 2 and sigma 3 over here. Alright, but because if it's 2D case, because this is 0 also, so our 2D is simply sigma theta and sigma zz, where this is 180, this is 90. So when you talk about it, sigma 1 is 180, where sigma 2 is 90 over here, and then sigma 3 is simply 0, nothing else, because we're talking about 2D case. 2D for a thin wall. Alright, and therefore once you solve for it, you just apply the formula, you can just get this value. And this value compared to your yield strength of your steel, you're actually far so-called smaller than your yield strength. So therefore your pressure vessel is safe. And lastly, state with justification what are finite element you will use to analyze the pipeline. Good job. I don't know. We'll think about it. But we'll just need to consider all these methods, size of crack, NDT method, and the coating that will prevent the direction of crack. Because 24.56 mm is actually quite small. Alright, the pin may actually cover it up and you may not see the crack. Things like that. Alright, so this is just a quick example, although it's not like 10 minutes already. But anyway, so yeah, see you soon when I see you.